In this lesson, we're going to look at the sine curve, the cosine curve, and make sure that you understand the relationship between those two curves and periodic motion. The motion that we're going to look at is a movement around a circle. So you can think of a whole bunch of things in the real world that have rotational motion. You can think of Ferris wheels, paddle boats, fans, car tires, all sorts of different things that rotate. And when we have motion like that, we can actually model that with a curve. And we model it with a sine curve, and therefore it's called sinusoidal motion. So once we get through analyzing a circular motion, you will see where the sine and the cosine curves come from. All right, well, how do we get started? Well, let's go way back a little bit, and we'll start with some simple trigonometry. And the simple trig we're going to look at is the trigonometry with a right angle triangle. And hopefully you remember a little memory aid, and I'll write it down here. It was SOH, CA, TOA. And that helped us remember the three primary trigonometric ratios of sine, cosine, and tangent. So if I was to throw an angle in this corner here, well, hopefully you'd be able to tell me that there are three sides associated with this triangle, and you could label them adjacent, opposite, and hypotenuse. And that means that we could draw a relationship between this angle and the lengths of the opposite and the hypotenuse with the sine function. So I could actually write, I could say, okay, the sine of angle theta is going to be the length of the opposite side divided by the length of the hypotenuse. And that you could also say that the cosine of that angle is the adjacent side over the hypotenuse. Now, these two ratios are going to be important because we're going to take this triangle and we're going to put it inside of a circle. And we're going to use the triangle to help figure out the location of a point that is going around the outside of the circle. So let's do that. Now here's a circle, and this is called a unit circle. And the reason why it's called a unit circle is because it has a radius of 1. You can see that it is centered right at the origin at 0, 0 of our coordinate axes. And you can see that it has a radius of 1 over here on this right side. X has a value of 1, y is 0. Way up here at the top, x has a value of 0, y at 1, and similarly around the other side. So think of this circle as kind of like a paddle wheel, okay, on one of those old steam-powered paddle wheel boats you used to go up and down the Mississippi. So there's a circle, and imagine this is the paddle wheel on that boat. Well, let's take this circle and put that triangle in there, okay, that we had placed on the previous screen. So there's our triangle, okay? Now, one important thing. This is the unit circle, and that means that this hypotenuse is actually the radius of the circle. So what I'm going to do is I'm going to put that radius length in there. It's 1. Now with that angle put in the corner of the triangle, we can come up with some values to describe where this point right there at the tip of the triangle on the edge of the circle is. So this point would have an x and a y value, right? Okay, well, those x and y values would be pretty easy at these dots, right? Because we can see that the x value here is 1 and the y is 0. And up at the top, y is 1 when x is 0. Over here, we've got x negative 1. So those ones are easy. The ones that are hard are these ones in the middle. Well, consider this. For this angle, this is still the adjacent side, and this is still the opposite side. And if we wrote the sine ratio for this triangle, we would have the sine of that angle theta equals the opposite, O, over the hypotenuse. But wait a minute, the hypotenuse is 1 in the unit circle. So that makes this really, really simple. We can just say the sine of that angle, well, that's the length of the opposite side. That's this length right here. Well, similarly, if we look at the cosine, we could say that the cosine of this angle, and we know cosine is the adjacent side over, and again, it's over this hypotenuse, which was 1. That simplifies things a whole lot because now the cosine of this angle is equal to just A. And that is this length here. And what that means is that this point has an x value that is simply cosine of theta, because it's the length of the adjacent side to that angle. Well, the y value, or the height at that point, that is equal to the sine of theta. All right, so if we know the angle, then using the cosine and sine functions on our calculator, we could figure out how far over and how far up this point is. Well, knowing that information, knowing how far over and how far up can be represented by the cosine and the sine function, well, that's helpful because what if we did this? What if we started this angle theta right here? Okay, so we're going to start it right there. That's where the point's going to start. And then what we're going to do is we're going to take this point here and we're going to move it in this direction all the way around the circle. Okay? Now, this angle here will start out very small. It'll start out at 0 and it will increase so that right here it will have the value of 90. If we keep going all the way to here, well, there is 180. Keep going a little more, we'll get to 270. And finally, when we come all the way around, we will be at 360 degrees. We will have gone all the way around the circle. Okay? Well, what would that look like if we were to graph that? Well, let's think of this unit circle here in a bit of a different light. Okay, so here's our unit circle, and what I'm going to do is I'm going to take and I'm going to make an x-axis at the same level that this x-axis is. I'm going to put a y-axis in right there. Now what I'm going to measure on the x-axis is the degree. That is, how far around the circle have we gone? Okay, so we'll start at 0 and we will end, once we've gone around one complete revolution, we've done 360. So halfway through would be 180, quarter of the way through would be 90, and 3/4 would be 270. Okay, well, let's take a good look at this. What is the, if this is a unit circle, which it is, what is the highest point right here? How high could we get up there? Well, this level here, which is the highest level we could ever get, well, that would have a height of 1 because it's the unit circle. Similarly, down here, the lowest we would ever get to go is down here, and that is at a measurement of -1. Okay? All right. So how do we graph this? Well, here's what I want you to imagine. Let's first graph the sine function. Okay? Imagine that this is a paddle wheel, and here's the level of the water. Okay? And the paddle wheel is going to rotate in this direction. We're going to go around the paddle wheel. And you're going to start right here at 0. Okay? Now imagine that you grabbed onto the paddle wheel. And it immediately, because it's rotating in that direction, it started to lift you up and out of the water. Okay? As you were stuck to the paddle wheel. If we took some snapshots of you, some pictures of you at certain points around your trip around the paddle wheel, then we could plot your height, right, as it relates to the angle that you've gone through. So for example, we start right here at a height of 0. That's when you got, stuck to the paddle wheel. Well, if we waited a little while, you would eventually make it up to here, right? And that would be the highest you would reach. Now, when does that happen? How many degrees did you have to go through to get to your maximum height? And we know that this is a right angle here between the axes, so 90 degrees was traveled and you hit your maximum height. Well, now you're coming down the other side of the paddle wheel. You're actually heading down here. When would you hit the water? How many degrees would it take for you to touch the water again? And it would be another 90 degrees, 90 to get up, 90 to come back down. So that means you would actually touch the water here at 180. Time to hold your breath. You are now being dragged underwater, and you would get to a depth of this -1 after 270 degrees. And finally, you would be able to open your mouth and breathe again and reach the surface of the water after you have completed one full revolution. Okay? So this picture, which is a nice smooth curve, that is the curve that is describing your height. How high out of the water or under the water are you? And if you remember, well, when we were talking about the point xy, the y value, which is your height on the y-axis, that was the sine. So the sine function. So this picture, which starts at 0, up to a maximum at 90, back down, hit 0, -1, and back to 0, that is the standard sine function, the basic sine function. And it is the sine function that is generated by moving an angle through 360 degrees on the unit circle. Okay? Well, what if you weren't interested with your height out of the water? What if rather you were interested with what your distance was away from the middle of the wheel? That is, this distance in here, or this distance here. Well, that's the x value, right? And we know that from their point xy, the x value was the cosine function. Well, let's see what that would look like. So, when we first got stuck on the paddle wheel, right here, how far away are we from the middle of the wheel? Okay, relatively speaking. We are 1 away. So we actually start right here. Okay, we have a value of 1. Now, as we move here, as we rotate around, notice that this distance here is shrinking. And when we actually hit the top, we have lined up perfectly with the middle of the wheel. So at 90 degrees, we are right here. We are 0 away from the middle of the wheel. Now, as we keep transitioning this way around the circle, we will hit our maximum of 1 away, this time in the negative direction from the middle of the wheel, at 180. So we'd be right there. Keep going, holding your breath, but here you are lined up again, right with the middle of the wheel. No horizontal distance away from it. You're right directly underneath the axle. So you are 0 away from it. And then finally, as you catch your breath again at the start, you are back to your maximum distance away from the middle of the wheel, the axle, so you are 1 away. Well, this here creates another curve. And this curve is the cosine curve. And you notice that the sine and the cosine look identical. The only difference is they have been shifted a little bit. And that's true. They are both sinusoidal, that is, they both share the same shape. The cosine is shaped like a sine function, but they are out of phase, if you like. by 90 degrees. So if we slid the cosine function over by 90 degrees, let's say we moved it this way by 90, these would all line up and the two curves would be right on top of each other. Okay, so if you imagine a paddle wheel going around and you being stuck on the outside of the paddle wheel, if we graph that motion, that's how we get this curvy motion where you are on the water, under the water, back up high above the water, down there. And you can see how that would work on a Ferris wheel, on just a regular wheel, if you were relating height and the degree you've traveled. Okay, so let's take a look at the actual formal diagram of the sine function. So these are the formal sine and cosine functions. Again, how do you draw them? Well, the sine function, the red one, notice that it starts and it has 3 zeros at 0, 180, and 360. It has a maximum at 90 and a minimum at 270, and you sketch it with a nice smooth curve. The cosine function, well, it starts out a little differently. The cosine function starts at a maximum of 1, which means it's going to end at a maximum of 1. Halfway in between, it's at its bottom, and it transitions between its zeros right like that. So it starts up, goes down, and comes back up. Okay, so those are the graphs of the sine function and the cosine function. You should be able to graph both of these anytime you want. You should be able to just say the sine function, up, down, back, cosine function, starts up, goes down, back up, and know that those are the standard sine and cosine functions. Okay, so that's a relationship between those curves and rotational periodic motion.